Hi everyone, this is Zoe, and today I'm mainly going to introduce the concept of CAE, the Content Adaptive Encoding Based Intelligent Optimization. And I will introduce quite a few algorithms from a systematic perspective, especially for the encoder optimization of AV1. So here's the outline of my talk. I'm going to cover mainly five subtopics. So at the very beginning, I'm going to introduce what kind of machine learning or AI technologies that we can leverage for the AV1 encoder optimization. And from this slide, it can be seen that is for AV1 encoder optimization, especially for balancing the trade-off and achieve a good performance, balancing the encoder speed, coding efficiency, and visual quality. Mainly, we can look into the core codec optimization, leveraging the use of machine learning from different modules inside the AV1 encoder. And for example, we can try to look into the use of machine learning for mode selection, for gap structure selection, for RT model refinement, for partition pruning, transform size and kernel type selection, as well as for the restoration filter selection. On the other hand, we also like to see what kind of content analysis through the use of machine learning in the pre-processing stage, especially this stage is leveraged to conduct some content adaptation and categorization and combine the pre-processing. So the main purpose of the pre-processing is to improve the coding efficiency. And we will look into the modules also in more details. Lastly, we're also going to see what kind of machine learning tools beyond the scope of AV1 that can be leveraged or even developed to be considered for the next generation of the standard after AV1, for example, for the AV2. And so next topic is first look into the pre-processing, potentially for the optimization of AV1 encoding. For the pre-processing, for this stage, actually the topics here we discussed can be imposed or incorporated for any encoder optimization, not only for AV1 but also for 264, HEVC, or any other encoders. The reason we like to leverage pre-processing is right now all the codecs are handling quite variety of abundant video content. And for example, AV1 compared against its predecessor VP9 has included more than 100 new coding tools. And so the encoder process, if you just do a exhaustive search, it can be super complicated, and which really dragging down the encoding speed. So if for different content, we can try to quickly identify the appropriate coding tools inside AV1, then we can really speed up the encoder while achieving a good enough performance. For example, AV1 for the very first time incorporate the screen content coding tools in the main body. Then if we can differentiate quickly the current content is screen content or not, then we can apply the specific coding tools to encode the current video content. Another way that another perspective we leverage the use of pre-processing for coding efficiency for AV1 is, for example, the videos uploaded to YouTube, mainly UGC videos. And those videos may already include some artifacts like blocky artifacts and blur or quite noisy. And processing these videos in the prior stage before they are fed into the encoder could potentially improve the coding efficiency, meaning that it could potentially reduce the bit rate while obtaining a sufficient good visual quality. For example, here we can leverage the use of sharpening, denoising, and this preprocessing algorithms. And we can use machine learning type of algorithm together with traditional image processing and to really remove those perceptually insignificant portion within the video content, while, for example, enhancing those perceptually significant areas and really help facilitate the encoder. For example, here we mentioned the region of interest, like for video conferencing, and the faces areas could be identified easily as a significant area. And also, we also mentioned that for frame level adaptive encoding, and then, for example, within the GAP structure, the open source of AI1 encoders many times leverage a hierarchical coding structure for a GAP structure. And within this GAP structure, there's a different layers of frame. And so how to intelligently allocate bits across different frames and even within different areas within the same frame. And like we just mentioned, how to allocate bits to more to those more significant visually important to human eyes could really leverage the use of machine learning, because these technologies could learn from could be trained and then could learn from the content analysis algorithms to facilitate the coding efficiency and to help achieve a good performance for the encoder. So leveraging the preprocessing is pretty critical, especially for handling a variety of different video content for like UGCs, and also for perceptual coding. We can achieve a good rate control performance and could apply content adaptation algorithms. So we give also a couple of examples. And before that, we compare using our own AV1 encoder with the use of content adaptive encoding preprocessing and without the use of preprocessing. So in this table, we apply to the same core encoder, but with and without the use of preprocessing to the same content, the same test set. So this test set we include 10 video clips, and with so majority is a 1080p video. There's one 4K. So the results show that with the use of preprocessing is actually can largely help reduce the bitrate. So we overall on average we achieved a more than 17% bitrate saving. At the same time, measuring by the objective quality matrix VMAP, we also obtain a VMAP score increment over 2. So it can be seen that generally it has been widely acknowledged the use of VMAP can well aligned with the subjective quality evaluation, the judgment. So hence can be seen that the use of preprocessing can really facilitate the encoding. And in particularly in this sample, we present the result for AV1 using our own Aurora 1 encoder. So next, we give a couple of examples. And the left image is just one of the frames of the the video content that has been encoded using Aurora One without the use of CE preprocessing. So this video is 1080p, and we present the bitrate and also VMAP scores. So by just judging of the subjective quality, can be seen that the right figure that as a result of the use of the preprocessing shows sharpening and also more brightful and visually more pleasant scene compared to the left one. And overall for this example, we achieve more than 17% and also a VMAP increment by 2. Another example is similar, and the red figures has a lot of textures and edges. It can be seen that is after with a bit rate of more than 20% saving, it definitely seen that the red figure that uses the preprocessing has presented pretty sharply image, especially for those textures in the costume. So next, we like to look into the core codec optimization for AV1 to see that what kind of machine learning technologies we can leverage down there. Specifically for AV1, like we mentioned, it has included many coding tools. And in this slide, we show that there's quite some modules for the core codec that can leverage the use of machine learning to really help improve the overall performance concerning the balancing the trade-off between encoder speed and coding efficiency. So we will take the open source AV1 encoder, namely LibOM as example. And we would suggest that for anyone who are interested in the use of machine learning for AV1 encoder optimization, you can simply download the code base of LibOM and basically search the keyword of neural networks in the submission comments. Then there's a lot of code that you can directly learn regarding how to use machine learning for AV1 encoder optimization. And we also give an example here specifically, which I think could be a good representation of the use of machine learning also for the encoding of other modules inside the AV1 encoder. So the example we are giving is we look into the transform type and the transform, basically the kernel type and the transform size selection through the use of machine learning. And here, this is a commit message that is for LibOM. And we'll look into the details down here through this slide. And for anyone who's interested in this work, we also present the paper in this slide. You can look at this is an IC paper that was presented last year. And we let's look at the machine learning algorithms essentials. So basically here, a neural network that has been incorporated for both the transform type and transform kernel pruning in order to speed up the AV1 encoder. And we know that in AV1 there's for example, for the transform size, it's closely related to the partition size, and for inside the partition size, then the transform size can be further determined, identified. So a neural network that can be leveraged for encoding, usually not so complicated neural network can achieve a very decent result. So here it is shown that is one hidden layer many times can really work well. And within the hidden layer, quite not that many nodes. For example, for up to 8 to 32 nodes could be enough for the hidden layer to achieve a good result. And to basically prune the transform size at the early stage, or for the transform kernels or transform type, and AV1 is a two-dimensional transform, the horizontal and vertical. In each dimension, there are 4 transform kernels that can be selected from, namely the DST, ADST, the flip ADST plus identical transform. And because there's a two-dimension, 4x4 is altogether 16 transform kernels that can be basically evaluated and choose the best one for the current transform size. So by using the machine learning, it can be seen that from the right-hand tables, and overall, there's quite a speed up. For example, for the lower QP values, which is the higher bit rate scenario, and for lower resolution, more than actually close to 40% of speed up that can be achieved. At the same time, we observe very relatively neglectable coding efficient loss here that can be observed. So it can be seen that is the use of machine learning, through the use of very simple neural network structure can really facilitate the speed up the encoder of AV1 while having a quite limited code efficient loss, meaning that these set axioms are quite effective. And next, we like to look into a specific coding tool, namely film grain, because AV1 is the first standard that has included the film grain coding tool inside its main body. And in this slide, we gave the overall the workflow for the use of film grain. And we also recommend a paper authored by Andre Norden and Neil Brockback. And this is a paper published in 2018 that has a good overview regarding the film grain tool that has been included inside the AV1 standard. So in this workflow that's shown in this slide, it can be seen that there's 2 major steps for implementing the film grain coding tool in AV1. At the encoder side, there's a degrain process. First, the grain strength that need to be estimated, and then under the guidance of this grain strengths, the degrain process can be conducted. And after degrain, we know that is the video content will have a very large amount of high frequency component removed, and thus achieving a good coding efficiency. And on the decoder side, because the grain strength is explicitly written to the bit stream, and which can be further recovered on the decoder and guide the thin set of film grain at the decoder side. So this is how the film grain that can help achieving at the same time good visual quality, still recovering or reconstructing the grain in the original signal, but also achieving good coding efficiency. So to better leverage the film grain, because it's quite challenging when we leverage the using of this tool, because in AV1 the film grain tool is implemented through the autoregression, and then there's a limited number of autoregression code efficiency we can play with. And the degrain process is basically a denoising process. Together with after the encoder, we many times end up with banding artifacts. At the same time, because different blocks inside the video frame can have a different characteristics as a result of encoding. Across the temporal layer, there's also some inconsistency because different frames are encoded in different ways. So sometimes, besides banding artifacts, we also may observe the inconsistency of the thin set grain patterns in the temporal domain, or even inside the same frame. we observed the inconsistent across different areas. Hence, how to best leverage the use of this AV1 coding tool, we also propose the use of machine learning as a facilitation um, to uh, to better leverage this coding to achieve a good visual quality, while also really leverage the use of this coding to achieve a coding efficiency. So from different several perspectives presented in this slide, we mentioned that how to maintain a great green consistency both spatially and temporally, and how to synthesize a green that's fidel pattern-wise to that present in the original signal, and also how to resolve the banding artifact to implement a good debanding algorithms from different perspectives shown in this figure. For example, the region-based green processing and green strength estimation from smooth areas. That is very critical. Then the problem will come to how to identify the smooth areas within a frame, and also the banding artifact simulation through the use of dithering and adaptive gap structure, adaptive temporal filtering strength together with adaptive QP assignment. All this that we can leverage the use of machine learning to achieve a better result. So we here gave a couple of examples, and this is we just get the dither algorithm directly from the open source AV1 encoder the LibM, and the use of the dither is right after the degrain and before the encoder. So the use of dithering is mainly targeted to reduce the banding artifacts as a result of debanding plus encoding, and this dithering we can see that is mainly we compare the before pre-dither and after dither Y channel. It can be seen that the dither algorithm used down here is mainly just add noise all over this frame. And on the other hand, after we use the dither in our algorithm, we mainly try to add dither on those edge area and also for those gradually changing area, and for those flat area where the adjacent frames actually present very close pixel values, we don't add much dither noise instead. This way, the adjacent frames could present a lot of similarity, which will help a good the motion composition and also help reduce the code efficiency while do a good dither algorithms overall to achieve a better visual quality. And we also give example for applying the use of film grain with two different AV1 encoders to the sequence of dinner scene. It is 1080p 60 frames, and we also gave the here in this slide we use the command line shown in the bottom to use the LibM AOM ink encoder to encode. Not sure, but encoded as 1.586 back per second. It's just looking at closely, there's still banding artifacts shown down here. And with adaptive area, for example, we mentioned that we try to estimate the noise level from the smooth areas. It can be seen that we can use less, close to 10% less bitrate, but achieving a very good, relatively good debanding result, showing that in the flat area, the banding artifacts has been largely ameliorated. And lastly, we like to see that what can be the use of machine learning can be further leveraged for the AV2 standard. So AV2 is already in the horizon, and we just like to see that the machine learning whether that can help. So from the two algorithms, two perspectives. So one is this one is we show the result of the end-to-end neural video coding completely replace the traditional two-dimensional plus motion estimation framework, but still this end-to-end still follow the use of different neural networks for intra-frame and for inter-frame. The result we have already included in our one of our invited paper that has been submitted to the proceedings of IEEE. And from the result, it can be seen that the end-to-end neural video coding just uses stacks, convolutional neural networks show a great potential that close to, for example, the 265 HEVC called the O-intro. And in this way, we just want to see that there's a potential that to use the counter-adaptive for intro and leverage the use of machine learning can get close to the result of the traditional video encoders. And another one, we show the use of machine learning, and actually this is can be leveraged at the post-processing stage. So after the decoding, and usually because of use of gap structure, and there's always some quality variations across different frames. So the use of machine learning can greatly try to help to borrow the good quality from that high quality frames and try to get enhancement of those relatively low quality frames. And by using the use of machine learning, we can see that is after the enhancement, both visual quality can be achieved. Also, on the side, objective quality wise, there is close to on our test side, somewhere between 8 and 20% of increment in the PSNR can be achieved. So that's include my talk. We have covered the use of machine learning to specifically 81 encode optimization for the improvement from different perspectives. And thank you for listening to my talk. You're welcome to send emails to me, and looking forward to more discussions down the road. Thank you.